Our last section of this chapter is going to be on current electricity. So we're going to start out with electric current. The variable is a capital I, and the definition is a flow of charged particles. Now, when we talk about the charged particles flowing, we're looking at a rate at which they can flow. So when we build our equation, we're going to have a capital I for current, and it's the rate at which those charges are flowing. So the charge is a Q, and then we're interested in how many charges can go in a second. So we're going to divide by time. For the units, we have a coulomb for charge and seconds for time, and this is called an ampere or an amp, so you can abbreviate that if you want to. And the symbol for an amp is a capital A. Now we are going to have a lab where we use an ammeter, and notice that it looks really similar to a voltmeter. We're just going to turn the dial to the current setting. And we'll use this ammeter to measure the current that flows through a circuit. So you'll actually get a digital readout when we hook that up to our batteries. The schematic diagram symbol for an ammeter is a capital A with a circle around it. And these two little lines represent the wires that we would hook up and plug into our ammeter. Now for current itself, there's no schematic diagram for electric current. However, you might see the direction indicated with arrows, and it would flow from the positive end of the battery to the negative end of the battery. So for our example problem, we have a little section of a wire, and there is 10 coulombs of current or charge flowing through every 2 seconds, and we're interested in the current. So we would set up our formula. The current is the amount of charge traveling in a certain amount of time, and the charge is going to be our coulombs. So we would simply plug in 10 coulombs for the charge, and we are told that that happens every 2 seconds. So 2 seconds is going to go in for the time, and then you don't even need to type that in your calculator. And we see that there's a current of 5 amps flowing in that particular section of the wire. Our next vocabulary term is resistance, and it's denoted with a capital R. And resistance is going to determine how much current can flow in a circuit. Now, we don't have a particular equation just for resistance because it's going to be used in other equations, particularly something called Ohm's Law that we'll get to. The unit for resistance is called an ohm, and we use the Greek letter capital omega to represent the symbol for the unit of an ohm. Now these pictures are all different types of resistors, and when we draw a picture or a schematic diagram of our circuit, a resistor is represented with little zigzags, and you can do them horizontally or vertically, and the number of zigzags does not matter. And in a lab that we're going to do before your next test, we will actually hook up these resistors instead of the light bulbs you've been working with, and then hook up our voltmeter and our ammeter and measure how much voltage is running in the circuit as well as how much current is going through the circuit. So here's just a picture for you with a joke on it. You can see if you can figure out that riddle. If not, you can always ask me about it in class if you can't figure it out. Next, we're going to look at Ohm's Law. So far we've talked about electric potential difference in a previous lesson, and then current and resistance in today's lesson. When we combine all of those together, we're going to come up with Ohm's Law. And you should have this website in your notes. I would go and visit that site and just read a little bit about Ohm's Law and circuits, and then it's got some practice problems for you. So I've got some facts listed for you, and then the important thing that we're going to look at is right here. The resistance is the ratio of the electric potential difference or voltage to the current, and that's where our formula is going to come from. You'll typically see Ohm's Law written as the electric potential difference, or voltage if you prefer that term, is going to be equal to current times resistance. And then over here, I wrote in the units. A volt in previous lesson, we had a volt equal to a joule over a coulomb. Well, with Ohm's Law, we can see that a volt is also equal to an amp times an ohm. And then we can rearrange this formula and write it in a few different ways. Or if you prefer to do that triangle, if that helps you with your equations, you can do that as well. So if that's something that helps you, feel free to write that down. And then I also have a little bit more facts for you that talks about direct or indirect relationships, so we can see if things are directly proportional or inversely proportional to each other. So if you want to pause the video and take a moment and write some of this down, you're welcome to do that. So we have a few example problems. For the first one, we've got an electrical device with a resistance of 3 ohms. So I'm going to put an R right here so I know that's my resistance. The current is 4 amps. This would be the I variable. And we are looking for a voltage drop of how many volts? So we're looking for the delta V. And you were told to use Ohm's Law, so we're going to set up that equation and plug in our numbers to solve. And you should be able to solve this without using a calculator. And we get an answer of 12 volts for this question. I'm going to switch colors now. For the next one, we have a voltage of 120 volts. This is our electric potential difference. So I'm going to go ahead and label that delta V. Next, we're told a current of 10 amps is going to flow through our heater, and we're looking for the resistance. So go ahead and use Ohm's Law and set that up. You can either rearrange first or plug in your numbers and then rearrange and come back and check your answer. So with this one, you should get a resistance of 12 ohms. And then finally, for part C, we have a flashlight that's powered by 3 volts. So volts is our voltage, or our electric potential difference, and a resistance of 60 ohms, and we're looking for the current. So pause the video and try this one and come back and check your answer. And you should have gotten 0.05 amps. So now that you've been learning the schematic diagram symbols for different components to a circuit, we're going to put all of those together. And I've got a few rules for you when you draw an entire schematic diagram for a whole circuit. It is a visual representation of that circuit using the symbols. Batteries and only batteries are going to be drawn on the left-hand side, and we're going to make the circuit into a boxy shape. So all the corners are going to be 90 degrees and no elements are drawn in the corners. So I have an example for you. We've got 2 batteries, a resistor, and an ammeter. So you always start out drawing the batteries, and you can write the plus and minus signs over here, or I could have put them on this side. It doesn't matter. It's a personal preference. Typically, you'll see them on the outside. But with 2 batteries, I want one long and one short line for one battery and a long and a short for the next battery. And then these are going to be my wires, and I want to make right angles, so 90-degree corners. And then I'm told there's a resistor, which in this case is going to be a little squiggly. And then also I need to put an ammeter in my circuit as well. And so I drew it as an A with a circle around it. Now the order, if it's not specified in a problem, the order in which I drew the resistor and the ammeter wouldn't matter. So I could have switched these up and drawn my ammeter first. I could also use this part of the box and put my resistor there. It's really up to you if there's no specification. So next we have 3 batteries. Remember, there's going to be a long line and a short line for each of the batteries. So I can go ahead and get that part done. And then a light bulb is just a circle. You should have seen that in our labs by now. And then a capacitor, if you remember, is 2 equal length lines. So I could draw a schematic that looks like this. Here's my 3 batteries. These are my light bulbs, and this is my capacitor. So the capacitor is going to be faced such that the wires make a 90-degree angle, or they're perpendicular to your capacitor lines. And you'll also see that this particular setup is what we call charging a capacitor. That's going to be in one of your labs if you haven't got to that yet. And remember, the order doesn't matter, so I just have a different example for you here. So I could have switched these around and put the light bulbs first and then put my capacitor later. Or I could have drawn all 3 elements on the same line over here. It doesn't matter if the order is not specified for you. And our last topic for this chapter is going to be electric power. Electric power is found by multiplying the current times the voltage. So if I look at my formula, I, in my head, call this the poison ivy formula because I have a P for power and then an IV for the current and the voltage. Technically, Yes, that voltage is an electric potential difference, a change in V. So if you want to continue to write the delta, feel free to do that. And then we've had power in a previous chapter, and hopefully you remember that the units for power was the watt, and you can abbreviate that with a capital W. Now for the next part of your notes, I have some substitutions to make using Ohm's Law. So you might see a case where you are given a voltage but not a current. We might have a resistance instead. So I could substitute in for the I on Ohm's Law. Remember, Ohm's Law looked like this. Or you can leave the delta sign off because it's implied when we say our voltage. So if I were to substitute in for the I, that would be V over R. And then I would still have times voltage from my original power equation. And when I combine those, I end up with V squared over R. So it's just another way to calculate the power. Or you might see using Ohm's Law substituting in for the V. So remember Ohm's Law, the V was equal to current times resistance. So I would still have the I from my power, and then current times resistance for my voltage, and when I combine those, I get I squared over R. So we can put all of these together into one big equation. So overall, if I'm looking for power, it really depends on what you're given in the problem. I can multiply current times voltage, or I can do voltage squared over resistance, or I can do current squared times resistance. Whichever one of these versions you choose is going to depend on what information is provided in the word problem. And then when you're solving for power, regardless of which version you use to calculate the power, the units are still going to be in watts. So we have an example problem. A digital clock has a resistance of 1.2 times 10 to the 4th ohms, and it's plugged into a 115 volt outlet. So I labeled the givens for you right here, and we're looking for the current. Current is going to be a capital I, and since I know voltage and resistance, I want to look for a formula that's got a V, an I, and an R in it, and hopefully you come up with Ohm's Law for that. From here, we can plug our numbers in and then solve for the current. And you should have gotten about 0.0096 amps, or since that's so small, I went ahead and showed you what the milliamps version would be if I move my decimal over. Now for part B, we're looking at how much power is being used. So I could do V squared over R. Now that I have a current, I can do I squared times R, or I can do I times V, the current times the voltage. That's the easier version, so since I found out what the current is, I'm going to go ahead and plug that in and use my answer from part A in for the current, and then we were told what the voltage was earlier. So go ahead and take a moment and calculate that. And you should get slightly over 1 watt for the power. That's it for the actual notes. I do have a couple of riddles for you, so if you want to hang in there and look and see if you can come up with the answers to these oh so hilarious riddles, we're going to do that next. So for this one, we're going to see that this guy is really, really cool because he's got his sunglasses on and a fancy haircut and his collar's flipped up, so he's cool. And then this was the symbol for an ohm. Oh, look, it's a coulomb, also known as a coulomb. Giggle, giggle. Next, we see that the letter C is missing. This is a bowl of fruit, but I'm going to subtract the RUIT part, and then I have an ohm. So look, it's C-foam. It's seafoam. Hilarious. Try this one. I know you secretly want to giggle. And then finally, our last one. Pause. Did you get it? So next time you're bored on a Saturday night, you don't have anything else to do, you can make funny physics puns. And then your friends will think you're awesome. That's it for this chapter. Hope you've enjoyed it.